Hello and welcome. This is an overview of a unit in trigonometry with some example problems. I think specifically there are 23 problems to be exact. It covers not a wide range, but it covers a range of right triangles all the way from Pythagorean Theorem to word problems including angles of elevation and depression. Now, a lot of the answers which I will give will also include the exact value, which to me is much more important than the approximated value, though the approximated value probably helps you make sense of what the final answer is. All right, let's go ahead and move on. Now, these are just scanned from a textbook here, so I'm sorry if I am clustered with my room. I'll go ahead and write out my solutions as I see fit, wherever I think I can fit them. So we have to find the value of each variable and leave our answers in simplest radical form. Now, before I begin, this part answers the question of somebody asking, do we use trig on this? The answer would, in this case, would be no. I'll tell you why in a second. And do we round to the nearest something? Do we use a decimal? The answer also is no. For the trig portion of it, although we're not doing it yet, we'll be using sine, cosine, and tangent. Those, unless you know what you're doing with the ratio, which in most cases I don't, you will not be getting a radical out. You'll be getting sine or cosine or tangent. So, and then as far as the decimal stuff, that's where we're only simplifying the radical. We are not writing out the decimal approximation. All right, let's go ahead and go straight into it. We have 7, 11, and x. This is a right triangle where the hypotenuse here is c and the legs are a and b. It doesn't matter which one you determine to be a and b as long as these are the legs. And we figure it out using a squared plus b squared equals c squared. So in simplifying it, you actually expand those squares and then you add them up and you get 170, I do believe. Now we're going to take the square root of it. So x is the square root of 170. Now the next goal is to try and break this number down. Now what this means here is I have the square root of something, and to simplify a square root, what I want to do is find factors of the number 170 that are perfect squares, because I can take the square root of them and pull them out. So my next step here is to try and think about what the largest perfect square value is that I can factor out of here. And to be honest, as I'm talking to you about it, I'm thinking about what there is, and I don't think there is anything. Let me try and run through this problem and show you what I mean. Pick two factors of 170, preferably perfect squares, but if you can't think too quickly on your feet about one, or if one doesn't exist, you won't be able to do that. So I can break this down into the square root of 10 times the square root of 17. Now 17 is a prime number, so I can't break that down farther. Here I keep breaking this down. I get the square root of 2 times the square root of 5 times the square root of 17. And these are all prime factors. Okay, so unless any of these, which they're prime factors so they can't be, but unless any of these numbers were perfect squares, or unless there were duplicates of any prime factors, it doesn't look like I could even break down the square root of 170 any farther than this. The second rule to simplifying a radical is to only have one radical in the end. In other words, this has 2 radicals, this has 3 radicals. Merge them back in together if they do not have any perfect square factors. The hope is that we do another problem that will have them so I can better explain it. Number 2. This time as we solve for x, it is actually one of the legs of your right triangle. So as you set up Pythagorean Theorem here, x is one of your legs. A squared plus b squared equals c squared. No problem. Moving on. And here we get 225. All right. X squared plus 169 is 225. X squared equals, oh boy, let's subtract that. Or let's add what number plus 60, no, 56. All right, 56. Okay, I know I can break this one down a little bit. So I'm going to take the square root of 56. Okay, so here's my ordeal. And I've preached this a lot in my class, so choose 2 factors of 56. Preferably choose 2 factors where one of them is a perfect square. So I'm going to start with 2 squared. The reason I don't start with 1 squared is because there's no reason to divide by 1 in this case, because I'll just end up with 56 again. But I want to see, and I'm not going to go any farther than this, definitely, but I want to see if I can divide 56 by 4, by 9, by 16, 25, I want to see if I can divide by any of them. The highest number that I choose is the most preferred. And I'll kind of show you 2 examples of what happens if you don't versus what happens if you do. Excuse me. And I think in this case, actually, 4 is the only one I can choose. Notice that I stopped at 36. I probably could have stopped at 25 or 16. I can divide 56 by 4. I cannot divide 56 by 9. I cannot by 16. 25, no. Now, the next perfect square is greater than half of 56. Because half of 56 is 28. There's no number that I can divide by 56 that is greater than 28 because, to get an integer out, because if I divide 56 by 28, I'll get 2. If I divide 56 by anything greater than 28, I'll get a number less than 2. And I'm not talking about 56. You'll get 1. I know that. But you want to split up these numbers into 2 different factors. So 36 would be out anyway. So 4 is the largest number I can divide 56 by. In which case, 56 divided by 4, I believe, is 14. So x is the square root of 4 times the square root of 14. The square root of 4 is 2. The entire purpose of doing this is that you take out any perfect squares that exist. Now the square root of 14 can be broken up into the square root of 7 times the square root of 2, but you'll end up in, like you did in this case here, all you get are prime factors, and none of them obviously are perfect squares, and none of them are duplicates. So this is the most simplified version of your answer. Now let's say you didn't go about it this way. Let's say you took the square root of 56. I'm going to go ahead and scroll down. Let's say we took the square root of 56, and like some of my students, they prefer to do prime factorization, which is completely fine. In some ways, actually, in many ways, you do know what you're doing still, but in some ways, you'll realize that there are faster ways, and as long as you know how to do them, it's probably for the better. The square root of 56, if you just keep, dividing by 2 or something that is, you know what I mean, something that's just an easy number, like as long as it's even, I know I can divide it by 2. If you just keep dividing by 2, I think you'll be good. Now I'm breaking up these into 2's like this. And the prime factorization of 56 is the square root of 2 times the square root of 2 times the square root of 2 times the square root of 7. So what someone can do here, this is specifically with square roots, is the square root of 2 times the square root of 2 is actually 2. So they can combine that. If you find any duplicates, go ahead and merge them together. You'll get the regular number out. And the square root of 2 times the square root of 7, once again, has to merge back together. For the sake of the rules of simplification, only have one radical in your answer. You still get 2 root 14. So that's another way of breaking it up. Now, although I will not be diving into cube roots in this video, I don't think at all, if this was the cube root of 56, it would divide like this. Like that. Cube root of 56 says what number times itself gives you 56. So the cube root of 56 equals the cube root, the cube root of 2 times the cube root of 2 times the cube root of 2 times the cube root of 7. Now when I said square roots is about finding 2 duplicates, the cube root's about finding 3 duplicates like this. So these would all merge together and give you 2. And this would be times the cube root of 7, like so. If you were to do it back again the way that I was referring to in the very beginning, what you want to do is find perfect cubes that you can factor out out of 56. For example, 2 cubed is 8, 3 cubed is 27, 4 cubed is obviously too big for this value. 27 is almost close to doubling itself to become 56, but it's not. So 8 is that other number that you can divide from 56 like so. So this can divide into the cube root of 8 times the cube root of 7. And the whole purpose of getting that cube root of 8 is because we can take the cube root of 8, that's 2. You'll get 2 times the cube root of 7. So multiple ways you can do these kinds of problems. This cube root stuff is not involved in Pythagorean Theorem. I just want to make sure that understanding what's happening when you're simplifying radicals kind of comes into play whenever you're doing these kinds of problems. Because I guess that's important. That's something that you carry from geometry into second-year algebra and stuff like that. This kind of practice and your familiarity with perfect squares and perfect cubes and perfect, I think the word is quartics, and stuff like that. Okay, moving on to number 3. Now 3 is a little different because you can't just use Pythagorean theorem. Well, I suppose you could, as long as you know what you're doing with it. In fact, I'm going to go and use Pythagorean theorem to kind of prove what's happening here, and then we'll go from there. Number 4 is going to be a little more difficult to use Pythagorean theorem, though of course you can still do it there too. I'll probably prove it that way. For the sake of time, I'll have to be a little conscious and see what it is I can or should do. Number 3, you only have one value that's known. These two are unknown. What you do know about these two values, though, based on these tick marks right here, is that these sides are congruent. So they might as well be the same thing, because they are. This is known as an isosceles right triangle, where the legs are congruent and the hypotenuse, of course, is longer. However, there's a special relationship with this, and even more specifically, because I'm going to dive into it later, in an isosceles right triangle, of course, the base angles are congruent. However, here they're both 45 degrees. So it's a relationship we're going to keep in mind. Okay, if these are both the same thing, why don't I just call this y and x as well? That way I can actually combine like terms in a way that I'd hope to. So if I use Pythagorean theorem, I will get 2x squared equals 121. Now I'll get x squared equals 121 over 2. Therefore, x equals the square root of 121 over 2. Now, we haven't practiced this kind of problem very much in my class, but considering we can split up a product into two roots, you can also do the same thing with a fraction. You cannot do the same thing with a sum or a quotient, but here in this case you can, like so. Now you can take the square root of 121, that is 11. And here you have root 2. I'm going to stop at this point just for 1 second to show you what the relationship is with an isosceles right triangle from its legs to its hypotenuse, or the other way around. There is a certain way that you can go about telling someone that you know exactly how much bigger a hypotenuse than its legs, or how much smaller a leg is than its hypotenuse, by doing a simple transformation. Here you saw 11 as your hypotenuse, and this number is 11 divided by root 2. Well, literally, to get from this number to this one, you divide by root 2. And someone might ask, well, that might be just coincidence. Does that always happen for every isosceles right triangle? Yes, it does. Every single time that you have an isosceles right triangle where you have 45 degrees, 90 degrees, as so, the leg is always root 2 times smaller than its hypotenuse, and obviously both legs are the same. Now, to get from the leg to the hypotenuse, you multiply by root 2 in the same fashion. So you can very quickly, if you recognize this scenario, you don't have to do this Pythagorean theorem right here and split this up. You can go straight to there and divide by root 2. Now, before I move on to the next problem, I'm actually not done solving this problem. The reason is because there's another simplification rule involving radicals, and that one says you may not have an irrational number in the denominator. We are going to do something called rationalizing the denominator. Okay. Now, it does exactly as it sounds. We are going to make the denominator rational. In other words, the number could be written as a fraction of an integer, a fraction of two integers. Granted, this will already be in a fraction. Now let's keep one thing in mind here. 11 divided by the square root of 2 is a rational number. Is an irrational number on its own. You just don't want this radical to show up in the denominator. So there's only really one way. Well, there's multiple things you can multiply it by but there's really only one way to go about it. First of all, it is not by squaring this value. Yes, when you square the value, you get 121 over 4 over 2. Gosh. 3, 2, 1, go. There's really only one way to go about this, and that's by multiplying this number by 1. And you say, well, won't that just be the same number? Yes, we want it to still be the same number. Though we do want to re-represent this number 1, because that's how we can re-represent this number as well. The way to multiply something by 1 is to multiply it by a number over itself. And as you saw earlier, when I was working on this, a different problem, which I think I deleted that work, but if you multiply the square root of 2 times the square root of 2, you're going to get 2. So on the bottom, you'll get 2. Now the whole purpose of doing this, as I said, was I get a rational number in the denominator. Whole purpose of doing it this way is I don't change the value. The square root of 2 divided by the square root of 2 is 1. So I am multiplying this number by 1, so I do not change its value. So this number becomes 11 root 2, all divided by 2. That's your final answer there. In fact, if you use your calculator, and it's only some scientific calculators that I really know that can actually do the thing, if I type 11 divided by root 2 in the calculator, it will simplify and show it this way, and you'll say, why did it change? Well, the value itself didn't change, but it just changed its look. It went straight from here to here, and the in-between process was multiplying by 1 or something that represents 1, so you can get this to be a rational number. Okay, number 4. Let's go ahead and do further proof with this one. This one's going to be a little more daunting to hear, so I would like you to hear me out and make sense of it. However, after some time, it kind of gets practiced and rehearsed so much that you kind of remember exactly what it is. What I'm first going to do is reflect this right triangle over this side right here. So I've created 2 isosceles right triangles. Furthermore, the entire blue triangle has a specific relationship with all the angles and all of its sides. This one was 30 degrees in the original right triangle, so this must be 60 degrees here. Therefore, this is also 60 degrees because those are congruent in that sense. And this one's also 30 because when I reflected it, that's the case. So 30 plus 30 is 60. So you have 60, 60, and 60, which is an equilateral triangle. Now an equiangular triangle. Now an equiangular triangle is also equilateral, which means all of these guys here are congruent. All of their values would be y. However, I'm going to represent them in terms of x for a very good reason. So all of these lengths are 2x. This is 2x, this is 2x, and this is 2x. Again, the reason being is that this is an equiangular or equilateral triangle. So all side lengths are the same. Now the reason I'm doing this in terms of x is so then I can say that y is taking the number x and doubling it. Okay, so that's a little bit easier to look at rather than x is 1/2 of y. In fact, when we talk about our ratio and relationship, which I still have to do over here, I'll be saying exactly that. So right now I'm going to change y into the value of 2x. Now I have the same like term here and here, and I have this length of 12. So what I can do is use Pythagorean Theorem again to solve for what x is. Therefore, I'll find out what these 2 lengths are. So this is a completely non-trigonometric, memorize this kind of formula thing. This is just using the relationship of the triangle that I know. Okay, so this is saying 12 squared plus x squared equals 2x, quantity squared. Now it's important that you square both the 2 and the x when it comes to this. So 144 plus x squared equals 2 squared is 4, x squared is x squared, and you have that right there. So 144 equals 3x squared. Divide both sides by 3. You'll get x squared equals 144 over 3. Take the square root like we did last time. X is the square root of 144 over 3. And we're back to the last thing that I did the last time, which is splitting up the fraction with 2 roots. And taking the square roots of them if they are perfect squares or something like that. This is 12 over root 3. Now, just like the other problem, we will rationalize the denominator. Before I do that, I want you to take a look at what this x value is with relation to how the 12 is being utilized. So here's your 12. X was 12 divided by root 3. Hint, hint, wink, wink, elbow nudge. If you want to get from the long leg of a right triangle whose angles are 30, 60, and 90 to the short leg of that right triangle, the one opposite 30, you divide your long leg's value by the square root of 3. Likewise, if you want to go from the short leg to the long leg to the one opposite of 60, you multiply by the square root of 3. And as you might have noticed right here, x to 2x, you would multiply this number by 2 to get there, and to go the other way back, you would divide this number by 2. So yes, all of these 2 triangles specifically, which I'll get into in a bit, 45, 45, 90, and 30, 60, 90, have special relationships and ratios that no other sets of triangles with like right triangles have. Like a 31 degree, 59 degree, 90 degree does not have that same kind of relationship, special thing that these ones do here. So these are things we're going to keep in mind, and I'll do that right after I finish solving this problem. Now, I do need to rationalize the denominator for this specific problem right here, so I have it in a better simplified format. So I will multiply this number by 1, or at least a representation of 1, which is root 3 over root 3. And this becomes 12 root 3, all divided by 3. Now, you can divide 3 from 12. So 12 divided by 3 is 4. So you will get 4 root 3 as your final answer. I should point it this way, actually. And some people might ask, how come we can't do root 3 divided by 3 and cancel it out? Well, first things first, because you're only going to divide out of one of these two things, not out of both of them. Even if it was 12 times 3 over 3, I'm going to choose to divide out of only one of them. I can either do 12 divided by 3, which is 4, or I can do 3 divided by 3, which is 1. And you'll still get the same answer. So you're only going to divide it once anyway. Now, how come I didn't choose to divide it from the root 3? Because the square root of 3 is kind of misleading. This number is not really 3, it's really the square root of 3. And the square root of 3 is about 1.7 something. So it's not even doing 3 divided by 3, it's 1.7 something divided by 3. So when dividing, only divide radicals with radicals, excuse me, and rational numbers with rational numbers, stuff like that. So your x value here is 4 root 3. This is 4 root 3. So as I double this number, as I multiply it by 2 to get what y is equal to, this length right here, I multiply 2 by 4 only, not by root 3, and I'll get 8 root 3. And that's your final length right there. So x is 4 root 3, y is 8 root 3, and there's your final. So, though I've spent a lot of time doing only 4 problems, this stuff must be known and understood. I'm going to make 2 triangles. They will look exactly the same, only they will not be. One will have 45 degrees, and 90 degrees. The other will have 30 degrees, 60 degrees, and 90 degrees. So as I just did up above, let's keep this thing in mind. When you have a 45, 45, 90 triangle, meaning this setup right here, the ratio of the legs to the hypotenuse is 1 to 1 to root 2. All that means is that every one of these triangles is similar. So as long as your legs are of some value, you will double either leg to get, I should do this in ratio form, you'll double either leg to get the hypotenuse value. And that one's perfectly as such. Not that these lengths are 1. Look, if this length was 10, this would be 10, 10, and 10 root 2. You would multiply everything by 10 because these triangles are similar. Now I have a 30, 60, 90 triangle. So in a 30, 60, 90, you have a similar kind of approach in terms of relationship. There's a little bit of a difference though. First of all, your 1 is only going to be represented on the side opposite 30 because it's the shortest leg. So that way, if I want to get hypotenuse, I just double that shortest leg, and that becomes 2. And if I take the shortest leg as well and want to get the longest leg, I multiply the shortest leg by root 3, and I get root 3. So this is 1 to 2 to root 3. Now this one's a little bit misleading and different in terms of how I'm writing it, because this is not leg to hypotenuse. This is leg to hypotenuse to leg. But in terms of using this as a way to, I guess, remember it, it's kind of easier to see the sequence as the numbers 1, 2, and 3, even though the number's not truly 3. One thing I guess you have to remember is that the square root of 3 is less than the value 2. What did I say the square root of 3 was before? It's about 1.7. 1.7 is less than 2. Now your hypotenuse always has to be your longest side, so there's no way that this could be 2 and this could be root 3 and have this thing still make sense. So just keeping that in mind, if you use this idea of 1 to 2 to root 3 in a 30, 60, 90, just make sure you know where things are placed. Now you can do this completely without that and completely without trig by doing exactly what I did, which was using Pythagorean Theorem in a different way. All right, there's 1 through 4. Okay, the lengths of 3 sides of a triangle are given. Describe each triangle as acute, right, or obtuse. Okay, so Pythagorean Theorem is a special relationship, which I did not prove, but it's a special relationship of the legs, the shorter sides of your triangle, and the hypotenuse, the longest side. where A is less than C and B is less than C. So what we consider to be our legs are the two shorter sides, and that makes sense. Pick the two shortest values in any of these, call those ones A and B, that way they can compare to C. This is for a right triangle right here. Now for an acute or obtuse triangle, there's a different kind of relationship that's involved. If you add a squared and b squared and you get a value that is greater than c squared, okay, it's a triangle where those lengths a and b, they're not longer than c, but when you add them up, it's greater than c. They are longer in their own respect, and it does make that hypotenuse shorter, which makes these two angle in a little bit more, if that kind of makes sense. If this had to be, this was the right angle before, now you get a, b, and c to dominate a little more. Now you have an acute triangle where all angles are less than 90. And then the final one is obtuse triangle, where if you add a and b, a squared and b squared, that's very important to know the difference. If you add a squared and b squared and you get a value that's less than c squared, that means c had lengthened itself to the point where a and b has to widen its angle in between to reach c, which makes this an obtuse triangle. So let's go ahead and do this in the best way possible. They kind of helped us out here by giving us what a and b should be, because they did this in ascending order. So if I labeled 9 as a, 10 as b, and 12 as c in the first example, I'm going to go ahead and add them and figure out what I get. So I'm just basically what I'm going to do here is compare 9 squared plus 10 squared to 12 squared. I don't know if they're equal or greater than or less than, so I'm going to leave that part blank. 9 squared is 81, 10 squared is 100, 12 squared is 144. As you can tell, we have 181 compared to 144. You are looking at something where 181 is greater than 144. Therefore, a squared plus b squared is greater than c squared, which makes this an acute triangle. This is number 5. Let's see if I can move this stuff up just a little bit. All of these a and b is less than c is still true for any of these three things, just so you know. Okay, number 6. Without going into too much detail, I already know the answer is a right triangle. Reason being, there are some special right triangles, some special Pythagorean triples that have a certain ratio. 8, 15, 17 is one of them. If you haven't heard that before, I'll write down a few of them for you. But it's something that just saves you time if you know what it is. Otherwise, otherwise just use Pythagorean Theorem. But it's just something you can kind of memorize. 8 squared is 64, 15 squared is 225, 17 squared is 289, and you do get 289 on the left and right. So these are equal. That does make this a right triangle. To move on to those Pythagorean triples, before I do number 7, here are 4 of them, the 4 smallest ones in terms of, I'm not sure what it's in terms of. I think just the numbers being the smallest. There's an infinite amount. These are the only 4 I actually know. 3, 4, 5. Now what all this means is 3 squared plus 4 squared is 5 squared. 5, 12, 13. 8, 15, 17, the one we just did. And 7, 24, 25. Okay. What this means is that any triangle that is similar to these 4, and of course there are many other ones. I don't know off the top of my head what they are. Any triangles that are similar to these ones, including like 6, 8, 10, from a 3, 4, 5 as you double the numbers, or if I triple these ones, 24, 45, 51, stuff like that. This is still an 8, 15, 17. Any similar triangles to these ones are right triangles. Pythagorean triples, meaning that they are especially so where the numbers are not irrational anywhere. They are all integers. This should be times 3. So once again, you do this enough, you practice it, you'll know it. So like I said, these are the 4 quote-unquote smallest ones. So when I'm already looking at number 7, I already know it's not going to be a right triangle. Not because like, oh, it's possible. It's just because I already know these 4, and if I know that these are the smallest ones, 5, 6, 10 is already smaller than 5, 12, 13, much less 7, 24, 25. So I already know it's not going to be a right triangle. And probably for the sake of practice for these problems, I'm willing to bet it's probably obtuse because we already did an acute and a right one. Not a good way to think about it on a test, that, oh, they're going to test you with all different kinds of them. But as you're doing this, you might already connect those kinds of dots and say, yeah, well, you know, it might pan out. So I get 25 plus 36, and that's compared to 100. It looks like it'll be less than, which confirms my theory of this test doing it. Keep in mind, I haven't done these problems yet. I'm doing these with you right now. So a squared plus b squared is less than c squared. That does make that an obtuse triangle. All right, let's go. Express sine of b, cosine of b, and tangent of b as ratios. Okay, before I do this, let me quickly give some things out to you to help you out with trig. Remember the story of Sokotoa. If you were ever in my classroom hearing this, I told you a great story about King Fred and Queen Wilma and how they did this ritual, this dance. Well, they weren't before King Fred and Queen Wilma. They married and became that. And all this kind of stuff. And anyway, Queen's name ended up changing from Queen Wilma to Queen Sokotoa. Had to do with soaking her toe in a pond. That's kind of the way to remember the word. Now, the word helps you remember trig ratios. Okay, trigonometry is all about right triangles and a value that you can obtain from two specific sides, one side divided by another, a ratio, if you will. And the relationships are developed using sine, cosine, and tangent. Those words, all very bizarre to me as well, even though I've been hearing them for years, over a decade. And what do they actually mean? I don't know how they came up with the names. I'd have to look that up. Tangent, I do know a little more of. I'm not going to take that explanation into here. But there's a specific value. If you take the sine, now keep in mind, this is an angle symbol. When you take the sine of something, you're taking the sine and cosine and tangent of an angle measure. So when you hit sine 1, you're taking the sine of 1 degree. What your calculator does, I don't know specifically what the calculator does, but pretend like you're a calculator, and you say, I'm pretending like there's a right triangle where obviously one of the angles is 90 degrees, but one of the non-90 degree angles is 1 degree. And what I'm going to do is take the relation, and obviously the other one therefore is 89 degrees, but what I'm going to do there is take the ratio of two sides. For sine, it's taking the opposite, the side opposite angle 1 right here, and it's dividing it by the hypotenuse of the right triangle. I'm just giving you the example with an example, but this is going to be opposite over hypotenuse. I'm going to use 3-letter short things. It looks like everything here is 3 letters. So, ka, toa, sine, op, hip, all that kind of stuff. Cosine does something sort of similar. If it was doing angle 1, it would take the leg that is adjacent to 1, which is this one. Notice I didn't say side adjacent because that could have been the hypotenuse as well. And it's going to divide by the hypotenuse of the right triangle. So it's going to be adjacent over hypotenuse. The tangent, if I want to take the tangent of angle 1, takes the side opposite divided by the leg adjacent. So it goes opposite over adjacent. So a few things to keep in mind here. First of all, the only side types you will refer to are opposite, adjacent, and hypotenuse. They're all with respect to the angle to which you are referring, such as angle 1 versus angle 89. And these are used with this mnemonic device of Sokotoa. Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. Now I'll be doing more with these as I go on. I hope that they give us plenty of examples where I can even use the calculator to talk to you about them in terms of how you know whether your answer sounds right and all this other kind of stuff. Now these just ask you to represent them as ratios, which means all you have to do is find the exact value as a fraction, and if you must simplify the radical, please do so. Looks like I won't be taking the square root of 57 anytime soon. I think that's a prime number. Okay, the sine of b. What I'm going to do is write the sine of b as opposite divided by hypotenuse. Now the side opposite b is the one that goes this way right here. So that's 2 root 57. The hypotenuse is the one that's always opposite your right angle. Now a lot of times they might mislead you into thinking, oh, this is slanted, therefore this is hypotenuse. No, it's clearly the one opposite the 90 degrees. So if you have to redraw your right triangle so it's faced upwards like this, please do so. So your hypotenuse is 22. So this becomes 2 over 22 reduces to 1 over 11. So 1 times the square root of 57 is just root 57. This is divided by 11, like so. That is a simplified version of that answer, sine of b. Okay, cosine of b, and clearly you can see I'm running out of room here, so just try and follow along with everything I do. Cosine of b takes the leg adjacent right here, divided by the hypotenuse. Ca, C-A-H, adjacent over hypotenuse. So that's 16 divided by that all hypotenuse, which is 22. 16 over 22, when you divide by 8, reduces to 8 over 11, and I do believe that's as good as you can make that, and there's your ratio. Tangent of b. I'm going to use purple here. Tangent is opposite over adjacent. Opposite b over adjacent of b. So 2 root 57 over 16, which 2 over 16 reduces to 1 over 8, and 1 times root 57, once again, is root 57, so it's root 57 over 8. And there are your 3, sine, cosine, and tangent, written only as ratios. You can type these in the calculator and determine what the decimal is, but that is not what's being asked. They're not asking you to round that. Okay, let's do this one. I'll do it, I don't know if it's more quickly. Let's do it again. Sine, cosine, and tangent of b. Once again, here's your angle. So everything with respect to the angle. The side, because, okay, keep this in mind. The side opposite b is root 33. The side opposite a is 4. So when I take the sine of a compared to the sine of b, I will get a different value for the very reason that the calculator is looking at the angle to which you're referring. So I'm referring to b here. So sine of b over here is root 33 over 7. Opposite over hypotenuse. That cannot reduce. Cosine of b is adjacent to b over hypotenuse, which is 4 over 7. It also cannot reduce. The tangent of b is opposite over adjacent. This problem was easier in the sense that nothing could reduce. I don't know why they didn't do this one first. But that's it. That's all I can do with those 3 right there. Now, let me give you one more example. I'm going to give you the tangent of a in this one, because there's possibly more you're going to have to do. In this case, I know there is. This would be 4 over the square root of 33. This is a fine ratio and all, but it's not simplified. So I'd have to multiply by root 33 over root 33. And yeah, that seems kind of weird, which is 4 root 33 over 33. That would be your final answer for that one, as far as the ratio that they would want, because that is a simplified radical. 4 divided by root 33 cannot reduce. However, this is more simplified than that, even though I agree it does not look cleaner. It is the more proper solution. Okay, find each missing value to the nearest tenth. So I'll have to write this underneath, I guess. I'll rewrite it. Now the tangent of blank, I'll go ahead and just put an x inside there. Okay, time to talk about right triangles a little bit more here to get the general idea of what's happening in these. I'm taking the tangent of an angle measure and I'm getting this value 1.11. Now keep in mind that the tangent of an angle is opposite divided by adjacent. Okay, I'm just giving you the full picture. There's a much easier way to solve this, which we're going to do. This is just to give you the full picture of what's actually going on. Opposite over adjacent. That means in a right triangle, let's say that your angle is this guy right here, and you're doing this number divided by this number. Now your opposite over adjacent in this case happens to be 1.11. So you can think of that as 1.11 divided by 1, which might mean that if you do opposite over adjacent, your opposite value might be 1.11, and your adjacent might be 1. These might be the actual values of the triangle. But keep in mind, you're trying to find an angle measure here that represents this. So if this ratio is always the same, then this angle will always be the same regardless of what these side lengths actually are. It means this doesn't have to be 1.11 and 1. What if I multiplied them by 100? It could be 111, and it could be 100. These could have been the original side lengths. I have no idea what they were. The fact of the matter is, I don't care. I care what the ratio is, because this angle will still be the same regardless of what these are, as long as they maintain the ratio. Now, what does all of this have to do with anything? Well, that, and also double checking your work. I know that my angle will be greater than 45 degrees. Here's how I know this. In an isosceles right triangle, these two lengths are the same. Let's say it was 100 and 100. That would mean this would be 45 degrees. Exactly. So would this one. Well, I did make mention before of the side opposite larger angles is bigger than the side opposite shorter angles. So if this side is larger than this side, then and this angle opposite the side must be larger than the angle opposite this side, right here. And if when they're equal, this makes this 45 degrees. If this becomes greater as a side, this will become greater than 45 degrees. So just keep in mind when you solve for your final answer, make sure you know that if you get something less than 45 degrees, you might have done something wrong. Okay, let's solve for x. Now the reason I rewrote this here is I wanted to space out what all this thing has. Reason being, the only way to get x by itself is not dividing by tangent. This does not say the tangent or tangent times x, even though it might look like it. Tangent is a function, and you are applying this function to x, much like a square root. You apply a square root to something, you're not multiplying square root or something like that. It's not square root times a number. You are taking the square root of a number, so I'm taking the tangent of a number. Now, much like a square root, there is an inverse for that. That's squaring a number. Tangent's inverse is simply called inverse tangent. It looks like this. It looks like it says tangent to the negative first power. Yeah, sort of. But whatever you do to one side, you must do to the other side. This allows this stuff to cancel out right here. And this on this side gives you exactly that, inverse tangent of 1.11. So if you take the tangent of a value, it is finding the ratio of an angle measure. If you take the inverse tangent of a value, it is finding the angle measure for that ratio. So if I go to my calculator and I type inverse tangent of 1.11, I'm going to get, let's see what they said, round to the nearest tenth. I'm going to get approximately, well, it's 47.984. 47.98 rounded to the nearest tenth becomes 48.0. That answer is in degrees. So that number is greater than 45, so that kind of checks out. So that checks out for me, and I think I'm good from there. So again, 1.11 was a ratio. I take the inverse tangent to find the angle measure that represents that ratio. So this angle measure is 48 degrees. If they ask you to find the other angle measure, I could have done inverse tangent of 100 over 111, something like that. But I also know if this is 48 degrees, this must be 42 degrees. That was, I'll write it up here, 48.0. Rounded to the nearest tenth. Number 11. Now I have tangent of 18 equals blank over 87. Blank I'll call x. To solve for x, very simply, I'm going to multiply both sides by 87. That makes sense? Algebraically speaking, get x by itself. Do that stuff. This is 87 times the tangent of 18. Now, there are a lot of things I should be asking you to avoid when it comes to the calculation of this thing. Be careful not to write it like tangent of 18 times 87. There's not an issue writing the 87 after here. The issue is when you go to your calculator, you don't want to multiply 87 by 18. You want to multiply 87 times by the tangent of 18. There are two different numbers there. So I have 87 times the tangent of 18 in my calculator becomes 28.26, which rounds to 28.3. Okay, this answer is not in degrees. This is a side length. Okay. Now let's see if this one makes sense. The tangent of 18. 18 is a pretty small angle with respect to what's happening here. You're comparing it to the numbers 90 and I guess the number 72. That must be the other angle measure. So if you're doing opposite over adjacent in this case right here, the opposite number should be smaller because it's the one that's opposite of 18. And the one adjacent to 18 is the one that's opposite of 72. So that does make sense that the 87 value is larger and that I got such a small number compared to that of 87. Now keep in mind there is no such relationship ratio that's like 18 over 82 equals 28.3 over 87. Doesn't over 72. equals 28.3 over 87. It doesn't work like angle divided by angle equals side length over side length. This is where we get our ratios and relationships. They don't grow similarly in that fashion otherwise. Number 12, sine of 34 equals 5 over, oh, let's see, 28.3. 5 over blank. So, sine of 34. 25? Oh, 5. 5 over blank, I can call that blank x. I'll do this problem this one way this one time. Afterward, if there are any other problems like it, it doesn't look like there is immediately, I will do it very quickly from here. Algebraically, I must get x by itself and in the numerator. So my first step might as well be multiplying both sides by x. X's cancel. Over there, on this side, you'll get x times the sine of 34 equals 5. Divide both sides by sine of 34 to get x by itself. That's a 4. So the sine of 34's cancel out on the left side, and on the right side you'll get x equals on the right side 5 over sine of 34. That's an exact answer. Use that to your calculator. Notice how every single time I do this problem, or these kinds of problems, before I get to my calculator, I make sure I find the exact answer for x. Please, please, please don't skip out on that for many reasons, of which I have not yet run into, with the one exception of potentially typing something wrong in your calculator. If you write it the right way here, you'll probably type it in your calculator correct. Okay, so there's the approximated answer there. It's 8.9. I'm not going to see if it makes sense. It does. But taking a look at that, there is kind of a simpler process, and yeah, it's kind of a magic tricky way to talk about things. It is saying, how do I quickly go from this step to this step? And if you notice, the x and the sine of 34 swapped. It's something that only really takes place in this kind of problem, where you're solving for a variable in its denominator, multiply both sides by that, divide both sides by that, they end up swapping, like so. It did not come into play on this problem right here. I don't swap the x and the tangent of 18. Okay, so don't just do it just because you think you should. Do it when you have practiced this enough and you understand what it is that's happening. And then I calculated my answer. Okay, number 13, sine of an angle is 0.996. Same kind of thing as number 10, only it is sine, and the number is now less than 1, as it should be. I'll explain why in a moment. Sine of x is 0.996. Now remember, 0.996 is a ratio. This ratio, SO in SOHCAHTOA, is opposite over hypotenuse, which is, in this case, 0.996 over 1. Or it might be 996 over 1,000. Whatever it is, I know a few things about this. First of all, a sine of a value can never be greater than 1. That would be saying that your opposite side is greater than your hypotenuse, which is impossible. There is a slight way where your hypotenuse can be equal. Your opposite can be equal to your hypotenuse. It doesn't exist in a right triangle, and I don't think we run into it here. But it can never be greater than it. Opposite always has to be shorter, or possibly equal to. Second thing is that my opposite is very, very close to being the same as my hypotenuse, which means you're probably looking at a right triangle that looks a little bit more like this. And you're taking, if this is the right angle right here, you're taking a look at this angle right here, opposite over hypotenuse. They're very close to each other, which means your angle is very big and very close to 90 degrees. I can imagine, I have not done this problem yet, I can imagine that my answer will probably be 89 point something. It's just a guess, but I think that's a pretty good guess to make. Meaning, if I get an answer, for whatever reason you type something in your calculator wrong, if I get an answer of like 42, you know that something weird happened. So to solve for x, same thing as inverse tangent, you take the inverse sine, and this button does exist on your calculator, something I cannot do without my calculator. As you take the sine of a ratio to get an angle to get a ratio, you take the inverse sine of a ratio to get an angle. So inverse sine of 0.996, see, I wasn't quite right. It is 84.87, so 84.9. Should probably do the squiggly lines here. So I said close to 89 degrees. Wasn't quite right, but this number makes sense because it's so sharp right here. You know, this angle here, 84.9, this angle is 5.1 degrees. I'm sorry, this angle here is 5.1 degrees, 84.9. This is all definitely coming into play the way that I expected. 84.9. All right. 14. Cosine of your unknown angle is 12 over 15. Okay, so same idea as the other ones. Now, in most cases, I would ask you to either simplify your radical, or you may write this as an exact decimal. Simplify your radical. Simplify your ratio, your fraction. 12 over 13 also reduces to 4 over 5. It's also, as a decimal, is 0.8. So you type any of these in your calculator, you'll get the exact same thing. One thing that I happen to know, although this won't mean anything for me because I don't know what the angles are with respect to it, is this is the same as, I mentioned this before, a 3, 4, 5 special right triangle, like so. So what we're doing is we're taking the cosine of this angle right here in a 3, 4, 5. Not that it matters for this problem, but you practice this enough, you will be paying attention to that and making note of that. Okay, let's take the inverse cosine of this to solve what x is. Inverse cosine of 12 over 15 gives me about 36.86, so about 36.9 degrees. That was number 14. And number 15, last one. Okay, cosine of 76 equals an unknown over 24. Cosine of 76 equals x over 24. Cosine of 76 equals x over 24. Cosine of 76 equals x over 24. Gotcha. Solve for x, multiply both sides by 24. Look, I'm not going to be cute about it. It should be very quick to do. Now you might ask yourself, is this going to be greater than or less than 24? Well, cosine of 76, cosine of a big angle, let's pretend like this is your angle, was adjacent over hypotenuse. Adjacent should be smaller than opposite. So, well, duh. Well, duh is going to be less than 24. I'm not saying this right, because hypotenuse is 24. So 24 times cosine is 76. I was thinking of tangent. Is 5.8 about. Nice. And that is a length, not a degree. All right, we're getting some stuff done. 5.8. All right, so that's using the calculator, that's using those trig functions in ways that are pretty respectable, I suppose. Okay, numbers 16 through 19, we're going to find the value of x, round lengths to the nearest tenth, and angle measures to the nearest degree. So that's a whole number for those ones. Like number 16, we have to find the angle measure. Now this one's a drawing, so to some this is easier, to some it's harder. The harder thing about this one is you have to create the setup based on what you have. Easier thing is at the very least you already have the picture, so you know how to make sense of your answer. So let's start with setup in general. You could potentially solve for the hypotenuse and then use sine or cosine, but that would not only take longer, but I doubt that this is a whole number. And as I've already mentioned before, use exact numbers as your answers only. That's going to be your best bet for any of these particular problems. With respect to x, you have the side opposite and the leg adjacent to it. Opposite and adjacent, or adjacent and opposite, are used in TOA from SOHCAHTOA, which means we should be using tangent because the tangent of x will give us the ratio 6 over 7. So if I take the tangent of my angle, you get 6 over 7. And to find the angle, just like the previous problems, solve for x, get it by itself by taking the inverse tangent of both sides. It is highly, highly recommended that you do write this exact answer here. Whoops. This exact answer here before solving. Then you approximate it, because at the very least you can then use those numbers. And I get 40.6, which is about 41 degrees. That answer makes sense to me because when I'm looking at this with tangent, these are close to being equal but not exact. This one opposite x is less than the one opposite this angle. So this should be a little less than 45 degrees, and it is. Number 17. X is now a length. It's the length of the hypotenuse. And here I have the angle 40 to which I could be referring. I'm actually going to do it two different ways for you so you get the gist of answering a later question. The side opposite 40 is here, and this is the hypotenuse. So opposite and hypotenuse, we'll be using sine. So if I take the sine of 40 degrees, I'll be getting 12 over x, opposite over hypotenuse, as my relationship. If you keep in mind what I did last time algebraically, we multiplied both sides by x and divided both sides by sine of 40. It's the same thing as swapping them, so solving for x, you'll get 12 over the sine of 40. There's my exact answer, and the approximation, remember this is a length, not a degree, we'll do 12 over sine of 40. And this is 18.66, which is 18.7 units long. At the very least, it makes sense that it's greater than 12. It has to be because it's the hypotenuse and 12 is a leg. One thing I have not yet mentioned actually is that when using your calculator, make sure that the mode that you are calculating these are in degrees. There's another mode, there are multiple modes, but there's another one called radians that you should avoid using for this particular thing. When you're in pre-calc, you will be using radians, I think, and degrees. Until then, you are only using degrees. It's like using inches and kilometers. They are just two different units of the same kind of measurement. Okay, number 18. This is where some people get confused because of the way that the triangle's drawn. For whatever reason, just because this thing looks more slanted than anything else, people say, oh, that's the hypotenuse. This is not the hypotenuse. The hypotenuse is the one that's opposite the right angle, right there. So this is the hypotenuse. If you would like for me to redraw this, so you get a little bit more familiar with what you have there, it would look more like this. Okay, so there we go. We have 58 degrees here. We have the side adjacent, well, we have to find the side adjacent to 58, and we have the hypotenuse. This one we'll be using cosine. I did mention that I was going to do the other problem a different way. Let's do this problem a different way as well. I'm sorry that I skipped that one, but I'll make sure to do it this time. So the cosine of 58 degrees is x over 18. That's the ratio, that's the relationship. Let me also mention, some people hit cosine of 58 immediately, and you say, oh, that's the ratio. That's fine, just don't round your number beforehand. So that's why, once again, I get x by itself first, multiply both sides by 18, and then you can type it in. Because now I'm using the exact value to approximate from. I'm not using approximated values to find my exact value or approximate value. So this is about 9.53, which is about 9.5 units. Okay, I promised I'd do it a different way, so let's do that. What if, for whatever reason, what if you weren't either liking using cosine or you didn't like having to multiply, just whatever. What if you wanted to do this a different way? What I could also do is find this angle measure. And this is 90 minus 58, so that's going to be 32. So this is 32 degrees here. Now when I do this problem, I will be doing the sine of 32, because this x is opposite of 32, and this is still hypotenuse. So if I want to solve it this way, I'll be doing sine of 32. Keep in mind, this was sine of 90 minus 58. So sine and cosine do kind of work hand in hand by using the complement of your angle. Like I said, I do think this answers a later question. Although I haven't done these problems before, I have seen a couple of the problems already. So this is still x over 18. So, in other words, sine of 32 and cosine of 58 must be the same thing. Don't take my word for it. Try and plug it into your calculator and see if you get the same thing. So they are the same for the very reason that in the triangle they both work together and they both give you the same exact ratio. So I kind of answered a later question in that question there. It still gets you 9.5. Finally, number 19, you have multiple different ways you can go about this in multiple outlets. I would go for the easiest one possible, meaning the one that avoids 2 root 70. I'm not saying 2 root 70 is bad for this problem. I'm just saying that if you want to get less confusing, by all means go ahead and do that. So if this is x right here, and you want to find that angle, let's go ahead and use these sides, opposite over hypotenuse. So let's do sine. Let's take the sine of x, and we will get 9 over 19. Now keep in mind, I could have taken cosine of x, then I'd be using 2 root 70 over 19, or tangent of x and get 9 over 2 root 70. All of them should give you the same x value. This one avoids using 2 root 70 altogether, which for me I guess is better. If you take the inverse sine of both sides, you'd get x equals the inverse sine of 9 over 19. That's the exact answer, the approximate one to a nearest degree. Keep in mind, and also hopefully you're in degrees for this, is 28.27, so about 28 degrees. Okay, that would be true for any one of them. There. I think that's all I wanted to say with those ones, but keep SOHCAHTOA in mind. Get your setup, get your exact answer, then get your approximate answer after that. Okay, I have a few word problems here. Now these ones I did type out, either because they were scanned weird or whatever else. It looks a little better now. You can tell this one looks a lot cleaner than these ones here. These ones look like scans. A surveyor measuring the tallest tree in a park. By the way, this is angle of elevation, angle of depression. This is kind of one extra step more than these previous problems. Now what we have to do is set up the right triangle that's involved in this, and we have to answer the question, not just solve for the unknown. We have to answer the question. A surveyor measuring the tallest tree in a park is 100 feet from the tree. So the surveyor is 100 feet from the tree. So what you can imagine for this problem immediately, before I keep reading on, is that here's this guy. Here's the tree. I don't really have brown. I guess here's brown. Here's the, yeah, sort of. Here's the tree. Okay. You don't have to draw these perfect. You don't have to draw a tree. Just make sure that you get a really good idea of what it is that you're looking at, though. And then here's his distance, which is 100 feet. Okay. Apparently this is the tallest tree in the park. His angle measuring device is 5 feet above the ground. The angle of elevation to the top of the tree is 48 degrees. How tall is the tree? I guess the only thing that they could have done better with this problem is recognize that the measuring device is technically probably 100 feet from the tree. Because if he's 100 feet from the tree and the measuring device is even a foot closer, then that would only be 99 feet from the tree. So let's pretend like this is the measuring device. I always draw like a tripod, even though that's not a tripod and it doesn't look anything like one. Here's the measuring device. It's 100 feet from the tree. Angle of elevation is all about, if he pointed this thing straight, that would be parallel to the ground. This should also be 100, this length right here. The angle of elevation is when you make this thing look up to the top of the tree. And I'll actually use my line tool for this right here. Angle of elevation is this guy right there to the top of the tree. So this is 48 degrees, not drawn to scale. And we'd like to know how tall the tree is. So, a couple things come into play here. First of all, your right triangle is here, starting from here and going up to there. There's the right angle. This is an unknown that we could solve for, but this is not your final answer. Your final answer is how tall is the tree. That means including the ground, which also means that the measuring device, angle measuring device, which is 5 feet away from the ground, as it looks straight ahead, it would be looking straight ahead at something that's 5 feet from the ground as well. So as I find the entire height of the tree, it's going to be adding 5 to that x value, to that unknown that we have. But let's start with the right triangle. Let's use our trig, figure out x, then add 5 to it. So my setup, well, my drawing setup is like that. My trig setup is here's 48. I'm looking for the side opposite 48, and I know the side adjacent to 48, the leg adjacent to 48, so I'll be using tangent. So if I take the tangent of 48, I'll be getting x over 100. Therefore, x equals 100 times the tangent of 48. Now I could write out my answer right now, and in fact, even if I rounded it right now, it really wouldn't matter because all I'm doing is adding 5, not 5 point something. But get in the habit of getting exact answers first. If I want to add a 5 to both sides to get my exact answer, whoops, should we say plus 5? To get my exact height right here and to round straight from there, I'll go ahead and do that. So let's type in the calculator, 100 times tangent of 48, close parentheses, hit plus 5. I hit plus 6. Plus 5, and you get 116.06. It's about 116.1. Now the question was how many feet, or how tall is it? Answer is feet. It did not ask how much to round it to. I'll go with that. This would be an exact answer. How tall is the tree? Oh, it's 100 times tangent of 48 plus 5 feet. You know, normal stuff. Yeah, that doesn't sound normal. So, like I said, exact answers are good for some things, but making sense of your answer is probably a lot better. So that man must be pretty tall. No, like I said, this isn't drawn to scale. Even the degree. 48 is probably much more like that. All right, there's one problem. I think 2 to go, 2 word problems. 20 minutes after being launched, a hot air balloon has risen to an altitude of 300 meters. The pilot can still see the starting point on the ground at a 25-degree angle of depression. How many meters is the balloon from the starting point? So, okay, this one, for some of these problems, it's almost expected that you kind of know what the setup of something looks like. Let's see if this is more brown. Ugh, sort of. Let's say the launching pad is right here. Okay. Now the hot air balloon, I don't know what a launching pad for a hot air balloon looks like. Now the hot air balloon might not necessarily go straight up. In fact, at this point, it's not. Otherwise, this guy's angle of depression would be 90 degrees. When you're referring to angle of depression, what you're doing is you're looking at the place that you are. So I can pretend like this is your guy in the hot air balloon. Okay. He's in his big hot air balloon. I kind of forget what they look like. I hope like that, unless that's just a parachute. Whatever. I forget. There's his hot air balloon. Angle of depression works like this. Wherever you look straight out to, you know, at the horizon, parallel to the ground, like so, take that and start lowering your head a certain amount of degrees. That number of degrees is your angle of depression. So let's say this was the starting point, his launching pad right there. This here represents the angle of depression of 25 degrees. Now the question is, how many meters is the balloon from the starting point, which does not, so compared to that of the man in the tree is the closest point to the tree, and the closest point to the tree was the ground, because 100 is closer than whatever this is. In this case, closest point as well as distance from is in reference to his eyesight to that place. So this is the part that we don't yet know. This is the part that we're trying to figure out. Okay, to complete this right triangle of sorts, what I can do, you could draw it over here. You could. I just want to make better reference to other questions that might be asked in the context of this problem, like how tall is he, how high is he from the ground, stuff like that. Or how far away is the starting point from the ground that's right below where he is. So this is the right triangle right here, where this is your right angle. Okay, these parts are unknown, well, sort of. Actually, this part's not unknown. He is 300 meters above the ground, so this is also something you can use. So it's 300 meters above the ground right there. We want to know how far away he is directly from it, like where you'd have to go this way, because height matters in the distance in this case. We don't know this one, but I don't think this one matters too much. What we do need now is an angle within the triangle. So we can do this one of two ways. If this is a right angle, and these two guys, as I mentioned, are parallel, and that means this is also a right angle right here, from his eyesight to looking straight down from beneath him, which means these two are complementary right here, which means this is 25 plus what is 90, that gives you 65. So you could find out that one, say 65 there. But what you might be doing more of is, because these two lines are parallel, this guy acts as a transversal. So these two alternate interior angles, this one and this one, will be congruent, which means this one's also 25. Or, as you can tell, 65 plus 25 is still 90. So that still works out. So we found an angle. In fact, we found two angles. I'm going to go ahead and use this one. This is probably the one you would be using when you get to it. Excuse me. Here's 25. I have hiccups, so I might start hiccuping a lot. Here's 25. Here's the opposite 25, which is 300. Here's the hypotenuse, to which we need to find. So we will be using sine, opposite, and hypotenuse. Sine of 25 equals 300 over x. We have to find out how many meters he is from the starting point. Solve for x by swapping x and sine of 25. There's an exact answer. Let's get the approximated one that will make more sense of, because I don't even know what this number is, or what it's close to. I know it's greater than 300. It is 709.86, so about 709.9 meters. Hot air balloon man is about 709.9 meters away, which is a little more than 2,000 feet. So he's been going for 20 minutes. I don't know if that makes sense. Maybe it does. It's less than half a mile, so maybe. Yeah, that makes sense. Okay, 22. A 5-foot tall woman stands 15 feet from a statue. She must look up at an angle 60 degrees to see the top of the statue. How tall is the statue? So a statue might as well be the Statue of Liberty. Doesn't matter what it is. Here's your woman. She's kind of waving. Let's just do that. Here's your statue. I'll just make the statue a bigger version of her. There you go. This is kind of scary to look at. So there's your statue. She stands 5 feet. The woman stands 5 feet tall. When she looks up from the 5 feet that she's at. So keep in mind, that 5 feet matters. There's a difference between this angle and this angle right here. Okay? Between her and an ant or a snail looking at the ground. Now she is 15 feet from the statue. This is definitely not drawn to scale. Never go with my drawings as drawn to scale here. 15 feet from it. You can do it from the ground or from there, but the whole idea is that you're going to be doing the angle of elevation from here, so this is where your right triangle is going to be working, and hopefully you recognize this as an angle of elevation problem, despite the fact that they never actually mention that. Okay, when she looks up, that is the idea. When she was looking straight ahead, they say, look up. She goes, huh? The amount that she looked up is 60 degrees. And this height right here might matter, but how tall is the statue also matters. So this is pretty much akin to the number 20. This is a lot like number 20. So we must find this height in the end, as this is 5 right here. This is the unknown x, which we must use to find the height. This is yet again another tangent problem. So I'm kind of surprised they gave you this one because it's not much different from the previous problem we did. Tangent because we have opposite and adjacent, as so. Okay, and x is 15 times tangent of 60. And once again, it's also even 5 feet. That didn't even change either. That's why I feel more comfortable rushing through this problem a little more. Now, she has to look up 60 degrees. Now, if you're referring to tangent problems, I know that this answer should be more than 15 feet. Well, it should be more than 20 feet, because I'm also going to add 5 in the end. But x should be greater than 15, because, let me type that, because I'm doing 60 degrees, and 60 is more than 45. Not substantially, but it is enough more than 45. Oh, whoops, I have to, where's my classic? Actually, let's do this without a calculator, because this is 60, right? Here's what makes this problem a little different. Let's do this. I'm sorry, I got excited. Let's look at the special triangles one more time. What if you did this on a test without a calculator? Like, what if they didn't give you a calculator and said, do this on a test? So here's how this looks. This is 60. This is 15. This is probably a little more drawn to scale. This is unknown. Okay, in a right triangle, 30, 60, 90, if this length is 1, this is root 3, and this is 2, although the 2 won't matter here. To get from 15 to x, I have to multiply by root 3. Okay, remember that? So x is 15 root 3. Now, of course, I'm going to have to approximate this, it looks like in my calculator. X is 15 root 3. So x plus 5 is 15 root 3 plus 5. Okay. We do have to do it in the calculator. I know. I got so excited. I was like, I can actually do some of this without it. So it's about 30.98, so about 31 feet. Definitely more than 15 or 20. Okay, one more problem. Explain why the sine of x equals the cosine of 90 minus x. Include a diagram with your explanation. So I'm not going to type it out. I'm going to explain it by talking to you while drawing a triangle. We did do this once. This is the one that I said that we will make reference to later. All right, I have a right triangle here, sort of. If this is x degrees, first of all, if this is x degrees, this is its complement, which means 90 minus x gives you this angle. If this was 20, this is 70, for a good reason. If I want to take the sine of x, and I'll just go ahead and call this a, b, and c. If I call the sine of x, I'm going to get a over c. If you take the cosine of 90 minus x, you will also get a over c. So the ratio is the same, the value is the same. The reason is because, although they are referring to different angles, these are different trig functions, which do ratios with respect to the angle itself. Sine uses opposite over hypotenuse. Now that's opposite of x, which is a, over hypotenuse, which is c. Cosine of 90 minus x uses opposite, which is a, over hypotenuse, again, which is c. So they both reference the same thing. I mean, that's really as good of an explanation as you need. You just need to say that the ratios are the same. Which one did I do it for? I did it for this one right here. Cosine of 58 was the same as sine of 90 minus 58. X, 90 minus x. Right? Still gave you x over 18. It was still, whoops, it was still the same ratio. Okay, so that was the last problem. I don't have anything more for you. That was number 23. As long as you can explain that one, I think you'll be good to go. And that's it, and that's all. I hope this was pretty good and pretty in-depth, and you'll be pretty good with your trig, assuming you can do kinds of problems like this. Nicely done. Fiend!